Picture this. You open up a brand new application, you click a button that says log in with Google or link your GitHub, and boom, instantly your profile is set up. It almost feels like magic, right? But think about what actually just happened there. That new app securely grabbed your profile picture and your email address, but you never, not once, typed your actual password into their system. Well, this everyday action is powered by a truly vital protocol, one that completely revolutionized how we share our digital lives, protecting your most sensitive data while keeping the internet fast and connected.
So, welcome to this explainer. Today, we are going to crack open the absolute backbone of modern software security, and that is OAuth 2.0. As defined in RFC 6749, this protocol is literally running behind the scenes of almost everything you do online. And my goal today? I want to demystify it completely for you. We're going to break down all the complex jargon, visualize exactly how the data flows, and make these advanced security concepts incredibly simple to understand.
Okay, let's dive right into our roadmap for today. We're going to be covering the Valley Key concept, the 4 core roles, endpoints and tokens, the authorization code flow, PKCE and token validation, and finally, we'll look at OAuth versus OpenID Connect.
All right, let's kick things off with part 1, the Valley Key concept.
To really appreciate why we even need this protocol in the first place, we kind of have to remember the terrifying early days of the internet. Back then, if a new app wanted to, say, import your contacts, it would literally just display a form asking you to type in your master email username and password. Seriously, if that new, untested app got hacked, the attacker instantly had the master keys to your entire digital life. It was an absolute security nightmare. So OAuth 2.0 was created to solve exactly this dilemma. At its heart, you have to remember, it's not an authentication protocol meant to prove who you are. It's a delegation protocol. Think of it exactly like a valet key for your car. When you pull up to a nice restaurant, you don't hand the valet your master key ring, right? The one that opens your front door, your office, and your car's glove box? No way. Instead, you hand them a special, limited valet key. It can start the engine and park the car, but it definitely cannot unlock the trunk. OAuth 2.0 does exactly this. It issues digital valet keys, which we call tokens, letting apps do a very specific job without ever seeing your master password.
Moving right along to section 2, the 4 core roles.
You know, to understand any secure system, you really need to know exactly who is playing on the field. The official specification, RFC 6749, outlines 4 core roles that make up this whole architectural foundation. Let's map these technical terms right onto a real-world office scenario to make it easy. First up, we have the resource owner. That's the boss. That is you, the human sitting at the browser who actually owns the data. Next is the client. Think of this as the assistant, the application that's asking for permission to access a file. Then we have the resource server. This is the filing cabinet. It's the backend database that's actually holding your protected data, and it demands a valid token before it opens up. And finally, the authorization server. This is the security guard. It's the central engine that verifies your identity and actually issues those valet keys to the client. Now, this brings us to how we handle different types of assistants, or client applications. Because, let's face it, not every app can be trusted with a secret password. So we divide them into 2 camps. First, we have confidential clients. These are secure backend servers, like a Node.js or Java application running in a locked-down private cloud. Because end users cannot look at the source code, these clients can safely hold a static password, known as a client_secret. On the flip side, we have public clients. These are your mobile apps downloaded to your phone or single-page applications running right there in your browser. A clever user can easily inspect the code or decompile a mobile app. Because of that, public clients simply cannot be trusted to hold a secret, and they require a totally different security approach.
Which leads us perfectly into section 3, endpoints and tokens.
So we have our players. But how do they actually talk to each other? Well, it happens over the public internet, which means it requires incredibly strict rules. The absolute baseline here is that all of this communication must happen over an encrypted TLS channel, which you probably just know as HTTPS. If you pass a valet key over unencrypted HTTP, anyone sitting on the same coffee shop Wi-Fi could just snatch it right out of thin air. Now, when an app wants to get that valet key securely, it talks to the authorization server using 2 distinct pathways. First is the authorization endpoint. I like to think of this as the consumer-facing front door. It handles the human interaction. This is the exact web address where your browser gets redirected so you can log in, look at a consent screen, and click approve. But here's the trick. The actual valet key isn't handed out at the front door. That happens at the token endpoint. This is the programmatic backdoor. It's a secure server-to-server connection where the application quietly trades its approval codes for the actual security tokens completely hidden from the user interface. And when that backstage exchange happens, the server actually hands out two different types of tokens. The access token is your active valet key. The client attaches this to its requests to prove it has permission. But here's the catch. Access tokens expire very quickly, often in just 15 minutes. Why? Well, to keep a hacker's window of opportunity incredibly tiny if the token is somehow stolen. But obviously, we don't want to make you, the user, log back in every 15 minutes. That would be awful. And that is exactly where the refresh token comes in. It's a highly sensitive, long-lived token stored securely by the client app. When the access token dies, the app quietly takes the refresh token to the backend token endpoint and just gets a brand new access token, entirely seamlessly, without bothering you.
All right, part 4, the authorization code flow.
Let's put all these puzzle pieces together and see how this builds a virtually unhackable system. This right here is the authorization code flow, and it happens in 2 phases. Step 1, you click Connect. The client application immediately redirects your browser over to the auth server's front door. Step 2, you log in and you approve the access. Now, Step 3 is brilliant. The auth server does not give your browser the token. Instead, it redirects your browser back to the client app with a very short-lived, temporary code. Then Step 4, the browser passes that code to the client's backend server. Finally, the client's backend takes that code, uses its client_secret, and goes to the backend token endpoint to make the trade. The actual access token goes straight from server to server. It never even touches your vulnerable web browser.
But, as we know, the internet is full of bad actors. Imagine a true crime scenario for a second, where an attacker tricks your browser into clicking a fake authorization link, trying to secretly bind their malicious account to your session. To instantly detect and drop these intercepted or fake requests, we use a brilliant little defense mechanism called the state parameter. When the client app first redirects you, it generates a unique, cryptographically strong random string and sends it along for the ride. When the auth server redirects you back, it must echo that exact same string. The client app checks it. If the string matches, great, we're safe. If it doesn't match, the app immediately knows it's an attack, drops the request instantly, and locks the doors.
Let's move on to Section 5, PKCE and token validation.
Okay, so that standard flow we just talked about is perfect for confidential backend servers. But we still have a major question to answer. How do we secure mobile apps? Remember, mobile apps are public clients. They cannot safely hold a static client secret to make that backend trade. The answer here is a massive modern security upgrade called BKCE, often pronounced PIXE. Instead of a permanent, hard-coded secret, PKCE forces the mobile app to create a dynamic, one-time secret for every single login attempt. First, the app creates a random string called a code verifier. It mathematically scrambles it or hashes it into a code challenge. It sends that challenge to the auth server during the initial request. Later on, when the app wants to trade its code for the actual token, it sends the original, unscrambled code verifier. The server does the math, and if they match, it mathematically proves that the app asking for the token is the exact same app that started the request. This dynamic secret creation completely replaces the old insecure implicit flow for public apps. It's a real game changer. So, the crucial point is, once that token finally makes its way to the resource server, our filing cabinet, how does the server actually know the token is legitimate and hasn't been tampered with? Well, it uses one of 2 methods. Local verification is used when the token is a self-contained JSON Web Token, or JWT. The resource server uses public cryptographic keys to verify the signature completely offline. It's incredibly fast. The other method is token introspection. If the token is just an opaque, random string of characters, the resource server has to make a direct network call back to the security guard to ask, hey, is this token still active?
And finally, Section 6, OAuth versus OpenID Connect.
Listen, if you take away just one thing from this entire explainer, let it be this, because it addresses the absolute biggest misconception developers have. Is OAuth 2.0 a login protocol? The answer is no. This is your ultimate memory hook right here. OAuth 2.0 strictly handles authorization. It gives the application a key card to unlock a door and access data. It dictates what the app can do, but it has absolutely no idea who you are. It doesn't provide any standardized way for the app to know your name. To fix this, OpenID Connect was built. OpenID Connect handles authentication. It gives the application an ID badge showing your name, your photograph, and your email.
The beautiful thing is, OpenID Connect isn't a replacement. It sits directly on top of the OAuth 2.0 architecture we just learned about. It just introduces a few brilliant additions. When the app makes its request, it includes a mandatory scope called OpenID. In response, alongside our standard access token valet key, the auth server hands over a brand new standardized ID token. This ID token is formatted perfectly to deliver your specific user profile information straight to the client application, which allows that app to instantly say welcome back with your name and picture.
And there you have it. You now understand the profound mechanics making the modern internet secure, from valet keys to PKCE cryptography. So the next time you encounter a consent screen asking to link your account, you're going to know exactly how your data is being protected behind the scenes. So I'll leave you with this. Which app will you hand a digital valet key to next? Keep learning, stay curious, and thanks so much for joining me on this explainer.